find the relationship between the two integrals. Well, this is going to be very interesting. Not so much for me, because I think this is the third time I'm shooting this tutorial. So the relation between in and in minus 1 is something we need to establish. This is in, and that is in minus 1. So that is looking promising. Okay, not so much, because I wrote the wrong expression. Okay, well, it's not looking promising at all. But the thing is, we need to do something with in to make it look like in minus 1. And in this very specific case, there is something we can do. So how about we take away 1 from here, and we multiply by a minus bx cubed. That should work, right? So it kind of looks like I to the n minus 1, except for this lousy term. So what do we do next with this term? We break down into two terms. So I will distribute now and see what happens. I'll get a times a minus bx cubed to the n minus 1 plus, no, minus a minus bx cubed times bx cubed dx. But this is nice because I can write it as two different integrals. We already know that the integral is linear, so that is fine. And that looks a bit promising because this is our expression for in minus 1. So I can actually remove this part and write in minus 1. So this is in minus 1. Well, almost, right? There's a factor of a. But that should be fine. So in is equal to a times in minus 1 and minus this integral, which I will call k. So how do we compute k? Is a very good question to ask. Because it can be very, very tedious to try to compute k if you don't know what you're doing. So here's this. And how do we evaluate this integral? Let us not forget to write n minus 1 here, because I clearly am forgetting to write symbols everywhere, and that's not good. Now we see here that there's an inner function and there's an outer function. So this already is suggesting integration by substitution. But we should only proceed if the derivative of the inside function is inside the integral that I'm looking to compute. So just by looking, the derivative of a minus bx cubed is minus 3bx squared. Don't worry about the factors, the constants. We would like to have an x squared in our term here. And here we have a bit more than x squared. We have an x cubed. But that should be fine, because I can always write x cubed as x squared times x. Okay, then probably if I proceed with integration by parts, I can can integrate this part. So this would be my my dv, and this would be my u. Now remember, it's as follows. So this is dv. If this is dv, then here's what v is going to be. It's going to be it's going to be minus 1 over 3 times a minus bx cubed to the n divided by n. And I can check this by differentiating. So if I differentiate this, I will bring down the power, then I'll get minus 1, and then I'll multiply by the derivative of the inside function, which is minus 3 b x squared. The minus 3 will cancel with the minus 3, and I would get bx squared. So I checked my integral by taking the derivative, and everything looks fine. So this should be my derivative, or it should be my v. It should be my v. Then I multiply this by u, so I multiply this by x. And then I take away from it the integral of v multiplied by du. Now if x is equal to u, then dx is equal to du. Then it's nice. No, I do not like how this is like. Now x is equal to u, so dx is equal to du. So that's fine. Maybe I'll even factor out the n as well. And here, because we have two minuses, I can write this as a plus. Then I have the following setup, which includes what does it include? It includes an expression which we are familiar with. Do you see what this expression is? Yes, exactly. It's in. So let me put this on the side. What we have right now is an expression for in. So I'll proceed with finding the equivalent expression for k. I write this, and then I write 1 over 3n times in, because I can, and because this is actually the expression for in. It's a minus bx cubed to the n. But then what am I really missing here? Because there's something that I'm missing, and it could really hurt my progress here. Do you see it? It's the fact that k is a definite integral. So I need to always remember that it's a definite integral. And so since this is already integrated, then I would like to substitute x is equal to 0 and also x is equal to 1 to make more progress with the problem. So this is what we have. I still need to evaluate this from 1 to 0, 0 to 1. Now, if you would like to evaluate this part, then you need to plug in x is equal to 1, and then you plug in x is equal to 0. To save space, I'll just write x like this. Yeah, so we need to plug in x is equal to 1 and then take away x is equal to 0. It doesn't matter what x is equal to 0 is, because here you get a 0, so you're multiplying by 0. So it's something minus 0. What is this thing? I mean, just plug in 1, so you get minus 1/3 times a minus b to the n divided by n. Minus 0, so that's just a minus b to the n divided by n. And then we're adding 1 we're adding 1 over 3n of in. And now all together, what do we have? I think we agreed that this is the expression for in. I hope we do agree on this. Yeah. So this is true. And so instead of k, I will now put in this expression. So this expression is equal to k. Now careful with the minus sign. So I get plus here and a minus there. But guess what? There's an in here and there's an in there. Then probably I should add this in to both sides. Now this is a minus sign. Then in that case, if I add 3n to both sides, I get 1 plus 1 over 3n of in is equal to a in minus 1 added to that this expression, which I'll write like this for short. Because we're running short on space. It's a long problem. There you go. And then this is really just the answer to the question. Then you're probably wondering, why does this not look like any of the choices? And the answer to that is because the problem itself was incorrectly formulated. So in the problem, this term was supposed to get annihilated. So this term was supposed to be 0. How was this term going to be equal to 0? Well, that was going to happen if we had proper choice of x. So we wanted this expression to be equal to 0 when x is equal to 1. Or we would like to choose another value instead of 1, which will give us 0. So one thing, this is the answer to the exercise. Now, another note. The exercise was originally intended to solve this problem. So it was the integral from 0 to 1 of 1 minus x cubed to the n dx. So you plug in a is equal to 1 and b is equal to 1. Now if you plug in a is equal to 1 and b is equal to 1 here, you get that this term will be 0. So this is a is equal to 1. Now this is true, so I can apply the formula. Then in that case, I would have, instead of a, I would have 1, and here I would have 1 minus 1. This would be 0. Then in that case, this is the expression for in minus 1. You can check this yourself, of course. So the funny thing is that this problem has been there for the 3rd year now. So 3 years, and I don't think anyone has actually spotted that there's a mistake. So that is very, very interesting, because I remember when I first did this problem, well, I didn't do it. And when I looked at the solution, I didn't understand it, so I just let it go. But then now I cannot let it go because I have to explain it. So that is what happened. There was a mistake with the question. But if you take all the steps in the right directions, and if you follow the same trick, then you should be able to get this result, at least for this integral. And more generally, if you're doing this integral, then this is a very intense exercise with a lot of ideas. There are a lot of ideas. Imagine you have to do an integral where you have to do integration by parts, and for the integration part you have to do integration by substitution. That is already very intense for a side problem. So this wasn't even the main problem. The main problem was trying to simplify the expression using this methodology and this trick here. So I think it is both amazing and interesting how rich this problem is with ideas, but it's a shame, it's an absolute shame that at least the exercise itself was not correctly formulated, and as a result the correct answer can never be properly reached.